Okay, so somewhat embarrassingly, it has taken me many attempts to make this video. Um, I'm going to try to make this video. I'm going to go through the outline that we always do this, but there's going to be there's going to be a subtlety that has to be dealt with, and I'm not sure the best way to explain this subtlety. So I'm just going to sort of analyze this problem within our general paradigm, our general framework, and then try to explain how I'm going to sort of conceptualize and handle these kind of subtleties that pop up. Okay, it's not going to be the most efficient way. Once you know the end, once you know what happens at the end, once you see what's going on at the end, you will see that this is not the most efficient way of solving this problem, but it's the only way that I can, like, if I'm imagining myself thinking through this problem and I haven't seen before, I'm going to try to make a video that way. And like I said, it's not going to be the most efficient way, but it's just how I think through it, not having any information, pretending like I haven't had any information. Okay, so again, normal things. The equation is in the right form. I'm going to look at my Cauchy data. It's on the x-axis. That's my Cauchy curve. Now, the interesting thing here is that the initial distribution, the initial solution, u initially is going to be 1. It's going to be 1 as x goes from 0 to 1. So I'll do that here. And it's going to be 0 everywhere else. And I'm going to do these in different colors here. Okay, so initially, I know that u is going to be equal to 0 here. It's going to be equal to 1 here. And it's going to be equal to 0 here. Okay, so the characteristic equations, I'm just going to write those out real quick. There they are. And so now I'm going to solve these for each location. So if I have, if x naught is less than 0, my solution is going to be t of s is equal to s. Z of s, well, z dot is 0, and if I'm over there, z of 0 is 0, so z of s is 0, and then x of s is just going to be equal to x naught, because if z is 0, then x naught is 0. Or if z is 0, then x dot is 0. Okay, now I'm actually going to do the purple part first, or the purple part next. This is going to be when x naught is greater than 1. This is going to be similar to what we did for the orange part. We're going to have t of s is equal to s. Z of s is equal to 0. And x of s is equal to x naught. Okay, so let me go ahead and sketch these characteristics, and then I'll do the blue ones. So they're just going to be vertical lines like this. And then again, it'll be dashed going through the origin here. And, or not again, but similar to how I've done it before. And now the blue ones, again, I'll do dashed on the boundary here. Not the blue ones, the purple ones. I'll do dashed on the boundaries, and we're going to have vertical lines like this. Okay, now we're going to modify. So as the problem goes on, we're going to change how high we draw these characteristics. But just hang with me for a minute. And I know that u is going to be equal to 0 here. And I know u is going to be equal to 0 over here. Finally, for the blue guys, this is 0. These are characteristics that pass through the x. Whoops. These are characteristics. Okay. These are characteristics that pass through the x-axis, going through 0 and 1. Okay, so we're going to have t of s is equal to s. Z of s is going to be equal to 1, and so x of s is going to be equal to s plus x naught. Okay, so these are going to be 45-degree lines, 45-degree angle lines, and again, for the ones at the border, I will draw it dashed like this, and then we'll have something like this. Okay, and I know that for the blue characteristics, I know that u is equal to 1. Okay, so this is where we're at so far. Okay, I'm going to do this for several different values of t, but now for t equals 0, I just want to draw what the solution is going to look like for t is equal to 0. So this is just going to be the initial value. So this is the x-axis, this is the u-axis. I know the solution is going to be 0 on this part. It's going to be 1 on this part, and then it's going to be equal to 0 afterwards. Okay, that's what the solution looks like. All right, now if I come back up here, kind of doing this in tandem with the analysis, let's see if I can get I want to get a formula for the solution. So I know, so before I can do that, I need to do this sort of analysis. I need to think about what's going on with the characteristics. So I've got two things going on. I definitely have intersecting blue and purple characteristics. So I know that there will be a shock wave. So I know there's going to be a shock wave. And it looks like the shock wave is going to happen at some point where x is greater than 1 over in that area where the blue and the purple characteristics are matching. But notice what's also going to happen. I have this whole area here. Where there's no characteristics, so it looks like there's going to be some expansion wave. And it looks like the expansion is going to be in that wedge, and that's going to be where 0 is less than x is less than t. Okay, but now here's where a subtlety happens. Our normal way of thinking about an expansion wave is we're just going to look at a generic characteristic or at a generic line going through the origin, and we're going to kind of call that a characteristic. Okay, but now what's going to happen is we're going to have this one coming up here, and it's going to be intersecting with the purple characteristics. So I have this expansion wave thing that's happening, but the expansion wave characteristics are also running into to other characteristics. So I got to figure out what's going to happen there. So let me erase this yellow line. So I need to figure out what's going to happen there. But the way that I want to think about it, and this is where things get slightly confusing, here's how I'm going to think about it. I see that, look, this line, this dashed line right here meets the purple line right there when t is equal to 1. Okay, so I'm going to draw a little dashed line here where t is equal to 1. This is t is equal to 1. And what do I know? If I look below t is equal to 1, the expansion wave characteristics, like those characteristics right there, are not going to intersect with any other characteristics. I'm going to have an expansion wave when x is bigger than 1, because again, the blue and purple characteristics are intersecting there. And I'm going to have something happening right there. I'm going to have my expansion wave characteristics right here, and those characteristics are not going to intersect any other characteristics. So I can kind of analyze the problem using the normal tools that I have right now if t is less than or equal to 1. So let's see what happens here when t is less than or equal to 1. I'm going to do that by the first thing that I'm going to do is try to write what the solution is. So this is going to be for t less than or equal to 1. Right now we're just looking at t is less than or equal to 1. I'm going to have u of xt. Okay, and I know that it is going to be equal to 0 when x is less than 0. If I think about the blue part, the solution is going to be equal to 1 on the blue characteristics, but I'm going to have some shock wave. So I'm going to skip the expansion part. So for the blue part, it's going to be equal to 1, and this region is going to be when x is greater than t and when x is less than the shock wave, which I need to figure out. Okay, because the shock wave is going to go something like this, and I need to figure out what that shock wave is, but I'm just going to leave it there as shock wave in my piecewise solution now, and we'll figure out what it is later. Okay, and by later I mean just a moment. And it's going to be 0, the solution is going to be 0 when x is bigger than the shock. Okay, and so what's going to happen here? Well, this is going to be when we have 0 less than x less than t. This is going to be our expansion. Well, if you come down and see what's going to happen, the expansion is going to happen between the orange and the blue part. So the expansion is just going to be the linear interpolation from the orange part to the blue part. So this is going to be the linear interpolation from the orange part to the blue part. If we use other methods, this is going to be x over t. Okay, so like I said, there's two ways to think about it. It's either going to be there's two ways to think about it. One way is going to be the linear interpolation between the orange part and the blue part as t goes on. I'm going to draw a diagram for t bigger than 0 in just a moment. The other way to do it is the way we've thought about it before, which is if this is a characteristic, I know that the slope is going to be equal to the t dot over the x dot, which is 1 over x, or sorry, 1 over z. And if it passes through this generic point here, AB, the slope of that line is equal to b over a, and we solve this, we get z is equal to a over b on the characteristic, or u of xt is equal to x over t on that wedge there. Okay, so now this is what we have. Whoops. And now I want to figure out information about the shock wave. But notice what's going to be happening. I want to draw this. So this is for t is equal to 0. I want to see what happens for a different value of t. Let me get an idea of what's happening as t is increasing. So let me maybe show you what is going to happen when t is equal to 1/2. So this is the x-axis, this is the u-axis. Let's see what happens when t is equal to 1/2. Going back up here to our solution, the orange part is going to be 0 when x is less than 0. The blue part is going to be 1 when x is less than 1. Sorry, x is bigger than 1. So we're going to have this. Okay, so my pen stopped working and I forget exactly where I am, but I'm sketching what's happening when t is equal to 1/2. So the orange part is still going to be 0 here for x less than or equal to 0. It's going to be equal to 1. Let's say this is t is equal to 1/2. So if this is t is equal to 1/2, it's going to be 1 from here until wherever the shock location happens. And then it's going to be 0 afterwards. It's going to be 0 afterwards. And then the expansion wave is going to be looking like this. Okay. So this is where we are for t is equal to 1. So now what I want to do is I want to try to determine this shock location. And I'm going to do this using two methods. I'm going to use it, the method that we learned a method. I'm going to use that method first and then another method second. So if I use that method first, the method that we learned to begin with, remember we have that xs, so this is the shock. So s here means shock. So this is going to be a sort of a differential equation for the shock location. This is going to be the jump in q over the jump in u. And again, for this problem, for Berger's equation, q of u is equal to u squared, u squared over 2. And so this becomes u to the right plus u to the left. Okay, there's a simplification step here, so maybe I should explain that because I know I've done it in a video, but I actually don't remember if it's one of the previous versions of this video, one of the previous rough drafts of this video, or a different video altogether. So let me just go through this. So the jump in q is going to be q of u, q evaluated at u to the right of the shock. So it's going to be 1/2 ur squared minus 1/2 ul squared divided by the jump in u. So it's going to be u to the right minus u to the left. Now the top is a difference of squares and the bottom is one of those factors. So this ends up being 1/2 u to the right plus u to the left. Okay, and if I look at u to the right, the solution is 0. That's the purple part. U to the left, the solution is 1. So this is equal to 1/2. So xs of t is equal to 1/2 t. So this is a curve in the xt plane. That's why we're using x and t. It's going to be 1/2 t plus some constant. But I know that where does the shock first happen? Well, the shock first happens here when t is equal to 0 and x is equal to 1. So I'm going to use that to figure out what c is. So when x is equal to 1, t is equal to 0. So this is going to be 1/2 times 0 plus c. So c is equal to 1. So this is going to be equal to 1/2 t plus c. Okay, so this is method 1. This is the method that we already know about, using the RH condition. Okay, so let's look at another method, and this method is going to be based on conservation of mass. So it's a conservation equation. So u is a conserved quantity, meaning the integral of u at any time. For any time t, I know that the integral over the whole row line, we'll just say minus infinity to infinity, u of xt dx is equal to the integral is constant. So it's going to be equal to whatever it was at the beginning, u of x0 dx. And if I come up here and look at what's going on when t is equal to 0, well, remember this endpoint right here is 1, and this height is 1. So the integral of u of x0, the integral of this function is just going to be 1. It's the height of this rectangle here. So this is going to be equal to 1. Okay, so now this says t is equal to 1/2, but just imagine it as a generic value of t now. So we're going to say this is just going to be for some t that's greater than 0. Let's do it this way. We're going to have 0 less than t, and for now we're assuming everything is less than or equal to 1 as well. Okay, so x location wise, this is going to be a t, because remember that's where, if I come back up here, that's where the blue solution starts, when x is equal to t. So it's going to be like this, and so now the integral of this function has to be equal to 1. Okay, so let's figure out what the integral of this function is. Remember this height is 1. So this yellow triangle part is going to be 1/2 base times height, that's the area. So it's going to be 1/2 times t, that's the base, and the height is 1. So for 0 less than t less than or equal to 1, the area is going to be equal to 1/2 t. Okay, that gives me the yellow triangle part. Now the integral of the blue part, what is that going to be? Well, it's just going to be the base times the height. So it's going to be the shock location minus t times 1. So it's going to be plus xs of t minus t. This is the area for any t between 0 and 1. Okay, so now I'm going to equate these two. I'm going to have 1/2 t plus xs of t minus t is equal to 1. And if you solve this for xs, you're still going to get xs of t is equal to 1/2 t plus 1, just like we got up here. So that's good. So I'm calling this the conservation method. But observe that this method up here also relies on conservation. Okay, but if we start with a function that is compactly supported, this method works. I think this method is a little easier to use, but the right-hand side of the PDE has to be 0 to use this method. And also the initial integral has to be finite. Okay, so I can actually come up here and replace this. So I know my shock. I can now replace my shock. So this is going to be less than 1/2 t plus 1, and the purple part is going to be equal to 1, is going to be 0 when we have 1/2 t plus 1 is less than x. And again, so far all of this is for t less than or equal to 1. So let's see how we can analyze the problem when t is greater than or equal to 1. So let me begin by graphing the shock wave. So the shock wave is 1/2 t plus 1. So if I look at this as t as a function of x, it's going to be a slope. It's going to be a line that has a slope of 1 that goes through the point t is equal to 0 and x is equal to 1. I'm sorry, this is a slope of 2. Okay, and when I draw it, so the point here is going to be that so the scale is kind of off. This actually dashed line here should be, the dashed black line should be one thing lower, but I got the scale off. So what's going to happen, the slope of the blue lines is 1. The slope of this shock is going to be 2. So notice what's going to happen. Eventually, the shock is going to pass out of the blue area. It's going to pass out of the blue area, and it's going to be up here, something like this. Okay, so now if I look at this shock right here, well, the blue part is no longer the left-hand part, and the purple part might still be the right-hand part, but the blue part is definitely not going to be the left-hand part. So my analysis that I did below is not valid once the shock passes out of this blue characteristic region. So let me erase this little red line that goes past that. Okay, so I have something like this. This characteristic is going to stop right here. Okay, so let me come down here and make a little note here. Okay, this, actually I could use that. So note this is valid until the shock exits the blue area. Okay, now it's going to exit the blue area. So what is the equation for that blue dashed line where it exits? That equation is x is equal to t. What is the equation for the shock? It's x is equal to 1/2 t plus 1. So I want to know where these two shocks intersect. Let me make that look a little better. Okay, well, on the line, x is equal to t, so I'm just going to make this 1/2 x plus 1. Okay, and now this, if I solve this for x, I'm going to get x is equal to 2. And if x is equal to 2 and it's on the line, x is equal to t, t is also going to be equal to 2. So this is valid from time t equals 0 until time t is equal to 2. Okay, so now we have our first hint here that maybe actually everything that we've done so far is not going to be just valid for t less than or equal to 1. Maybe it's actually going to be valid for t less than or equal to 2. And let's come back up to our diagram and see what's happening here. So this is the shock location. So remember, the reason that we were unsure about t less than or equal to 1 is because we're going to have a characteristic coming through like this. And now this yellow characteristic is meeting with the purple characteristic, but we also have this shock here, and it's not clear what's going to happen. Okay, but now notice what's going to happen. So this, I'm going to draw another dashed line. This dashed line is going to be when t is equal to 2. So everything that we've done so far seems valid for t less than or equal to 2. So notice that the purple characteristics, once they hit the red line, they don't continue, because on that side of the line, the solution is the blue solution. So let me erase some of these to make the picture look a little clearer about what's happening. So this will just go up like this. This one is just going to go up to here. Okay, but now we will have this one. This one is outside of the shock. It doesn't hit this shock, this part of the shock. So I'm going to leave that. And I just want to kind of erase that just a little bit. Okay, now something similar is going to be for these blue guys. So these blue guys are only going to go up into the shock. Okay, so the blue guys are only going to go up into the shock like this. And then these dashed lines don't exist. Okay, so now everything is good, and we even have this one. Okay, so now everything is good for t equal to 2. So now this solution is valid for t is greater than or equal to 2. If I draw the yellow characteristics are going to look like this. For now, I'm just going to draw them up to t is equal to 2. Oh. Sorry, I erased a little too much there. So the yellow characteristics, I'm just going to draw up to t is equal to 2 now. These are going to be the yellow characteristics. And note, these characteristics are not meeting with any of the purple characteristics for t less than or equal to 2. And this will be important for later. So notice this point right here. This point right here is going to be x. X is also equal to 2. So this point right here is x is equal to 2 and t is equal to 2. Okay, so now what I want to do is I want to look at the problem for t greater than or equal to 2. So now, after other consideration, we actually see that this is going to be valid for t less than or equal to 2. And before we move on, let's just give more information about why that's true. Notice if I plug in t is equal to 2 here, on the left-hand side, t is equal to 2, and on the right-hand side, 1/2 t plus 1 is going to be equal to 2. So what happens when t is equal to 2? What's going to happen when t is equal to 2? The linear part goes away. And let's actually come down here and graph what's going to happen, similar to how we've done it up there. So this is going to be for t is equal to 2. Well, the orange part is going to be orange all the way up here. The blue part is going to be equal to 1. So t is, well, let's do actually maybe t is equal to 1/2. So we can kind of see the progression. So 1.5. So t is equal to 3/2. This is going to be equal to 3/2 here. And it's going to be blue from here until the shock. So if t is equal to 3/2, if t is equal to 3/2, and I come up here to my shock and plug in t is equal to 3/2, I'm going to get 3/4 plus 1, which is 1.75. So this is going to be up here to 1.75, like this. And then it's going to be purple afterwards. So it's going to be 0 afterwards. And we're going to have the expansion wave like this. Okay. So this is actually pretty bad to scale. So let me fix this. Because I want to illustrate a specific thing that's happening. Okay, so let's say this is, whoops. So the pin is now just sort of deciding to not switch when I think I'm switching over here, and it kind of even gives me a response that it's shifting. Okay, so if t is equal to 3/2, let's say this, if I plug in 3/2 to my shock equation, this is going to be 1.75. And so the distance between these two is just going to be 0.25. So it's going to be equal to 1 there and 0 afterwards. And 0 afterwards, and then the linear interpolation between these two here. Okay, I'm not sure if this actually is working. Okay. All right, so now notice what's happening if I look at a generic value of t. Okay, so now let's just look at what's happening for a generic value of t. I'm not going to draw the axes, but what's going to happen, well, this orange part is going to be orange. Okay, now as t increases, what's going to happen? The blue part, the length of the blue part goes to 0. Okay, the length of the blue part goes to 0. When we get to t is equal to 2, this is going to be equal to 2. Now the blue part is just kind of a dot there, and the purple part is going to be 0 here, and the yellow part is going to interpolate like that. Okay, and so now we're going to have a shock that forms right here. Okay, so now if you look at what's going to happen for a generic value of, if I look at a generic value of t bigger than 0, so if I look at a generic value of t bigger than 0, or sorry, bigger than 2, So what's going to happen when t is bigger than 2? If I kind of extend this, this is going to extend off this way. The purple will kind of go this way. The angles aren't exactly right, but the point is we're going to have this part where the purple and the yellow overlap, and we're going to have a shock there. Okay, so let's do a little bit better job here. So what we're going to have now, this is going to be for t bigger than 2. Okay, we're going to have the orange part here. The formula for the yellow part is still going to be x over 2, and it's still going to be if we're still looking at it, it's going to be for x less than t. Okay, so if I come up here, let's say that this is going to be my t. Okay, the yellow part is going to be x over t, like this. Okay, now what's going to happen with the purple part? What's going to happen with the purple part? Well, the purple part, again, coming back up here to the formulas, the purple part is going to be equal to 0 for x bigger than this. So for x bigger than 1/2 t plus 1. But for this part, if t is bigger than 0, then 1/2 t plus 1 is less than t. Sorry, if t is bigger than 2, 1/2 t plus 1 is less than t. So we're going to have this, we're going to have the purple part being like this. And so we have this triple valuedness, and we're going to have some shock that we have to figure out. So in other words, what we're going to do, at some point, we're going to cut off the yellow line. We're going to cut off the yellow line, and at this point, there's going to be a jump discontinuity. The solution will be equal to x over t over here, and it'll be equal to 0 over here. And this location right here is going to be called the shock location. It's not going to be called this shock location. It is the shock location. Okay, and let's try to figure out what the shock location is, again, using the two different methods that we have. So one method is going to be xs dot of t is going to be equal to the jump in q over the jump in u. But now the value of the solution to the left of the shock is going to be x over 2, and the value to the left of to the right of the shock is 0. The value to the left of the shock is x over 2, x over t. So this is 1/2 times x over t. So notice now we actually have a differential equation. Like x is on both sides of the equation here. So we can write this as dxs over x is equal to 1/2 t dt. Take an antiderivative. We're going to get the natural log of the absolute value of x on the left-hand side is equal to 1/2 times the absolute value of the natural log of t plus some constant, or this is going to be equal to the natural log of the square root of t plus c. T is positive, so I'm okay with leaving it like that. Okay, exponentiating both sides, we're going to get, this is x sub s, we're going to get that x sub s of t is going to be equal to some constant times the square root of t. Okay, well, how can we find out what the constant is? So let's go back to our characteristic diagram. Okay, well, the shock location is first, like, what is the value of t where the shock location first happens? Well, it's going to be right here where t is equal to 2. So I know that the shock location first happens when t is equal to 2 and x is equal to 2. So if I come back down here, I'm going to have 2 is equal to xs of 2. And this is going to be a times the square root of 2. So a is equal to the square root of 2. So then this is going to be equal to the square root of 2t. Okay, so this is one method. Okay, let's do the other method, the conservation of mass method. So if we do the conservation of mass method, the area has to always equal to 1 because that's what the area was when we began. Okay, so what is the area here? Well, it's a triangle. What is the height of the triangle? Well, at this point right here, the value of the yellow line is going to be xs of t over t. And so the area of this triangle is going to be 1/2 times the height, which is xs of t over t, times the base, which is xs of t. Okay, so we come back down here. We're going to have 1 is equal to 1/2 xs squared of t over t. And again, solving this for xs, we're going to get xs squared of t is equal to 2t. And we're going to take the positive square root because it's positive, so xs of t is going to be equal to the square root of 2t. Okay, or if you want to think about this as t being a function of x, so this is the conservation of mass method. Again, the other one is based on that. So we want to think about this t being as a function of x, so we can think more about how to graph it. This is going to be t is equal to x squared over 2. Okay, if you come back up here and graph it, t is equal to x squared over 2. It's going to be a parabola that kind of goes up like this. Let me make that look a little bit better. It's going to be a parabola that goes up like this. Okay, so I might have the characteristics going like this. And then this one, this characteristic is not, it's going to meet it way higher up. Okay, and so now our solution for t greater than or equal to 2, we're going to have u of xt is going to be equal to the following. It's going to be equal to 0 when x is less than 0. It's going to be equal to x over t when we have 0 less than x. Less than, if we come down, I forget already what it is, square root of 2t. Oops. And then it's going to be equal to 0 for x less than or equal to or less than the square root of 2t with the discontinuity there. And we can even do, if we want, we could do less than or equal to there. Okay, so that's it for this problem. Again, I don't know if this was kind of the most efficient way to do it, but just sort of doing this problem from a blank slate, this is kind of the way that I would, not the way that I would think about it, this is exactly the way that I did think about this problem. I hope it's helped. I know this is an incredibly long video.